Oh, I had good Thanksgiving dinner yesterday. Turkey, potatoes. Oh, it's all gone. Delicious. And the best part was the dessert. 2 slices of chocolate pie. Delicious. I was kind of thinking that when I was driving in. Maybe I ate too much last night.
Yeah.
It can be. Not as nice as some other meats, maybe.
It's not soft. I soft as chicken.
It's maybe chicken's better. Yeah. Resistivity. Did you write that down? Yep. Oh. Continue. Yeah. Okay. So there's not actually a lot in this particular lesson. It's kind of just really one key formula. So last time we were talking about resistance, and we said if the resistance is bigger, then that means voltage is reduced when the charge passes through it. So for example, I said if we have a 1 ohm resistor, that it means a coulomb of charge that had a volt of voltage will lose that volt if it passes through a 1 ohm resistor. And by the way, where does that energy go, do you think? So the energy just doesn't disappear. Heat. The resistor produces heat. So in some ways resistors are like little heaters. In some ways. Okay. So all electrical devices, they offer resistance. Because if you think about it, when the charge passes through it, the charge does some work. It maybe makes light, it makes sound, so then the voltage reduces. So that's actually what a resistor is, reduces the voltage. The only difference is that these resistors are actually doing useful work, whereas a normal resistor just wasted energy. But these are actually doing useful work. So what exactly, we've talked a little bit about resistors. What exactly is a resistor? Well, resistor is an electrical device that offers a known fixed amount of resistance. Now, as I was saying yesterday, usually the resistance is fixed and constant, but actually, technically not. But roughly it is. So, normally the work done is heat, which is what I was just talking about. Small resistors are really just small heaters. And this is a picture of a resistor. So they're usually these small little cylinders, and when the current passes through it, the current loses some voltage, and it's wasted all as heat. Okay, so the only thing you really need from this slide is just even the picture of a resistor, so you know what they look like. Because one of our experiments we'll do next semester will involve resistors, so it is related to your experiment. So if you can just draw this and just say this is a resistor of fixed resistance. If you can just make a little diagram. Because actually the shape is important, because that's what we're going to go into next. Question, KJ?
Is it like this one?
Which one now? That's the other symbol. It is that. There's 2 symbols for resistors. I use the one that looks like a rectangle. We'll see that later. Don't worry. Okay, did you draw that, Jerry?
Yeah.
Continue?
Yeah.
So, what affects the level of resistance? How can we make the resistance bigger or smaller? So, for example, what do you think? If the resistor is longer, will that make more or less resistance?
More.
More resistance, yeah, because there's more of the resistor to pass through. Yeah. Now, next. Yes. What about the radius? Does that affect the resistance? Yeah. For the same reason. Different shape, different size. Yes. Does the type of material that's used?
Of course.
Well, of course, yeah. If you use copper or if you use gold or something like this, yeah. Yes, definitely. So, putting these together, we can actually get a formula for how much resistance there is in a resistor. Now, before you write this down, let me explain the formula. So this is the total resistance, and it depends on three things actually. It depends on the length. So, if it's longer, more resistance. It depends on the material. That's what this constant is. This is called the resistivity constant. And it also depends on the area, you know, how big it is. In fact, if the area is bigger, then that's less resistance. Makes it, yeah, I know it seems weird at first, but if you think about it, it's like if you have a hall and there's people traveling down a hall. If the hall is wider, then it offers less resistance to the people walking down it. So this is the formula for resistance, where L is the length, A is the cross-sectional area, and rho is a constant that is different for each material. It is called the resistivity of the material. And the definition of that? Resistivity measures how much an electrical conductor stops the flow of electricity through it. Most metals have a very low value, and the units used, what would be the units? If you rearrange this, what would be the units? Let's do that as a quick exercise before you write this down. Well, no, still loading. If we rearrange this in our head, L over A, what unit is L over A? That is meter over meter squared. So that's 1 over meter. If I bring that up to the left, I get meter ohms. So in other words, the units are ohm meters. That measures how much resistivity there is. Okay, so there's a lot here. I do actually need you to write both these definitions down fully. These are exam definitions that I have seen on the exam before.
Still, when we see the different resistance, they have same size. But formula for the resistivity is there, and they have same size, no different area, and no different length.
If they have the same length and the same area,
yeah,
and they're the same material,
yeah.
then they should.
I'm not sure about the material, but they have similar like 100 or 150 or.
I think what they do there, yeah, I know they all look the same shape. They must use either two things happen. Either they use a different material, or it looks like it's the same size, but maybe if you break it open, it's different on the inside. My guess though is it's a different material. What I would guess is perhaps there's two materials and they change the ratio of the mixture to increase or decrease it. Did you write both definitions down? All of them? Okay.
Teacher,
Yes.
what's the difference between MEPRE and MET?
Slow down. What's the difference between what?
MEPRE, meter,
Yeah.
and MEPR.
No, and there's another difference as well. You mean MET or E and MET ER? Yes. In here, If you write MET or E, that means 1 meter long. If you write MET or, that means measurement. So for example, ohm meter measures ohms. Voltmeter measures volts. Voltmeter? You know volts? Do you know volts?
No.
Amps? A, amps.
Ah.
V, volts.
Ah.
Do you know these? Jerry, do you know these?
No.
Can you say volts in Chinese?
Wow. Wow. Ah. Okay. Didn't say V at all.
No, but you need to know the word, Jerry. So, Jerry, voltmeter is a thing that measures volts. Ammeter is a thing that measures amps. Ohm meter measures ohms. Yeah? What do you mean no? No, do you understand?
Yeah.
Are you sure?
Yes.
So if I want something that measures a Jerry, I would use a Jerry meter. If I want something that measures a Sean,
You can't measure it.
I would use a Sean meter. Of course I can. If I want something that measures, what else do we have? Coffee meter. Yeah. ER. Yeah, so I say RE is meter length. So this is ohm meter, as in meter length. Yeah, only if we're in the States, which we are not. The Americans use ER. And I found out the reason why they use ER. Because they didn't want to use the French spelling. So they changed it. Because there was about 100 years ago or so, there was a movement in the States to reduce the influence of French on the English language. So that's why some of the spellings changed. Like we were talking about the S and the Z. It's to de-French the language. Yeah. Okay, did you write those definitions down? Yeah. Right. Let's go on. So we have our formula. Come on. Stuck. That's loading. There you go. Whoop, 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 whoop. Okay, so what is an insulator? You know this from chemistry, I hope. Something conducts, something heat. An insulator what? Yeah, but not quite actually.
Does not conduct anything.
No, that's worse. That's further away from the writing.
Right? Oh.
An insulator will offer an appreciable level of resistance, and what I mean by that is a lot of resistance. And you might say, hang on, I thought an insulator doesn't conduct. Well, not technically true. I mean, all things can be used as conductors. It's just a matter of how much. Yeah, like take this as an example. This is a good example. Wood, conductor or insulator?
Yeah,
Insulator. But if it's struck by a bolt of lightning, then it will be a conductor because the lightning will travel through the tree to hit the ground. Okay, so it's wrong to say it does not conduct. It's right to say that it's a very poor conductor because it has a lot of resistance. And often it has a high level of resistivity. So wood is a material that has a high constant for resistivity. So we call it an insulator. And a conductor, of course, then is the opposite. It will not offer an appreciable level of resistance and will often, not always, but will often have a low level of resistivity. And I think we talked about water. Water is considered a conductor or an insulator. Well, it's more of an insulator because it's a very poor conductor. It only becomes a better conductor if you add things to it like salt or stuff like this. Yeah, there's a lot of definitions in this lesson, only one formula. So you can write this. You have this, Chrissy? Yeah. Sean? Where are you? Okay. Jerry? Where are you? Chew! Ah, come on, Chew. Wait, what time is it? I shouldn't really let you in, but sit down. What happened to you? You sleep late as well? Who would sleep late? That's terrible. I would never oversleep. No. It's funny because the other maths teacher told me she overslept this morning as well. It's one of those mornings. Okay. Continue? Yep. Okay. So, now on to some values of resistivity. The first one is graphite that you would have in your pencil. And we consider this a conductor. And you see, very, very small resistivity constant. You can write these down. Carbon. This is carbon. You know carbon? It's a conductor. I don't know about diamonds, but I know the carbon in your pencil.
Yeah, no.
Yeah. Yeah, but carbon is very, very, very special because carbon's properties change depending on its structure.
Yeah.
So if you put carbon together one way, you make diamonds. If you put carbon together another way, you make people.
Yeah.
If you put carbon together another way, you make pencils. We're made of carbon. We're all carbon. Carbon and water. That's all we are. Yeah. Carbon and water. Yes. In fact, plastic is carbon. It's carbon. Yeah. And you all understand that plastic and people are very different, and so are diamonds. So carbon, when it's a graphite in a pencil, is a conductor. But I don't know, Sean, I feel like when it's in a diamond form, it's not a conductor. And when it's in human form, in people form,
Calm down.
yeah, I think so, a little bit, yeah. Okay, next material. Copper, we all know, is a conductor. Interestingly, which is a better conductor? Between these two. No, the carbon is better. Because Oh, sorry, no, I misread it. Apologies. The copper is better because it's lower value there. Okay, next material. Nickel. So nickel, similar to copper, similar. I think the big difference is nickel is cheaper than copper. Copper is actually kind of expensive. Copper is expensive enough that people steal copper from building sites. That's why it's important to lock it up. So, you know, when they're building a new road, they have all the street lamps. They have to be careful because people will, but before the roads open, in the night people will go to all the street lamps and pull out the copper wire. Because it's expensive enough to mean it's worth stealing. The church I used to go to in my last hometown, sometimes people would break in to steal the metals. You know, like if there's copper cups or things like that. So, copper is expensive. Nickel is a little bit cheaper. Yeah. Okay. Next is, I think this is even cheaper. Nichrome, which I think is nickel and chromium. It is a conductor. It's cheap. Not as good of a conductor as copper or nickel, but it's still good and it's still cheap. Got that? Yeah. Okay. Next material. So now we're on to the insulators and look at the big difference. It's quite clear it's different. A material like wood. Now really, there's a huge difference here because this is -6 and this is 14. That's 10 to the 20 different. So huge difference between a conductor and an insulator's resistivity constant. Okay, next material we'll have a look at is rubber. You all probably know rubber is an insulator. Like rubber in the car tire, the wheels of the car. Yeah. Yeah. Continue. Yeah. Okay. Now, technically, you could use any of these conductors to make an insulator, and any of these insulators to make a conductor, because it's not only the constant that affects the resistance, but also the length and the area. So by adjusting the length and the area, you could actually change a conductor into an insulator, or an insulator into a conductor. For example, what would happen to the resistance if you make the area smaller? If you think about the formula, what would happen? It would increase. So if I have copper, which is a conductor, but if I make it narrow enough, then it will behave more like an insulator because there will be much more resistance. Yeah. And of course the opposite is true for the insulators. If you make them thick enough, they can behave a bit like a conductor. For example, when a tree gets struck by a bolt of lightning, because the tree is thick, it can act like a conductor. Okay, so let's have a look at this example. Now, this is actually good because we're in this room. These electrical heaters, they're actually very, very simple machines. If you look inside of it, all this is, it's very, very simple. The current comes out here, and there is a resistor, a big resistor inside of it, made usually of nichrome. And this resistor, they have it wheeled around the base like this. So if you look at the bottom, the wire goes like this. And when the current passes through it, it warms up from the resistance, and actually the heat then rises up through the box. So this is actually really the simplest machine in your house. It's literally a piece of wire, that's all. A piece of wire that's at the bottom of a metal box. That's all it is. Nothing fancy. Nothing fancy. You could make one of these yourself easily. Really, really could. You just need nichrome. That's all you really need. So nichrome, when you have 20 centimeters and it's 5 millimeters in diameter, how much resistance is there? So we have to use the formula. We have to be careful. Millimeters and centimeters. So I'll give you a minute to calculate this. You'll need the table for nichrome.
Teacher,
Yes.
would we wear plastic gloves? If we touch high tension,
High voltage.
something
Yeah, don't.
like
I don't recommend it. It's what would happen, Jerry, I think, is when you touch it, it will get really hot and it will start to melt. So maybe you won't get electrocuted and die, but you might burn your hand because the plastic might melt onto your hand.
Well, it's through the air.
Say again?
Through the air.
Air.
Like what is real?
The lightning.
Yeah. It is through the air.
Through the air. Yeah, through the air. So even air can be a conductor. Yeah. You have it calculated?
Calculated.
Oh, dude.
Oh no, I calculated.
Okay.
Yeah. Sorry, in the
I know, too early, huh?
yeah.
Now, Monica, don't you feel nice and warm after your porridge? Nice and toasty? Don't worry, I'm not asking you to do anything. Just okay. Yeah. See, look at these guys, they're so cold. What do you have for breakfast?
Oats with chocolate milk.
Chocolate milk? That's breakfast? Okay.
With oats.
With ox? With ox, the meat.
No, O-A-K-S.
O-K-A-X.
O-A-K-S. What is it?
O-A-K-X. What the heck is that? What is that? What are you eating, dude? Is this where we discover a terrible secret about Andrew? Alright, do we have this calculated?
Yeah.
Oh!
Oh!
Yeah, sorry.
What is it?
That's what I have every day, as you see. That thing I was eating yesterday.
Isn't it porridge?
That is what we call oats in Ireland. Now, you learned some English. Yes, good, okay. Right, let's have a look here. Now, my calculator's not open. Do we all have answers? Do we all have answers? Yeah. Okay. Mr. Porridge, what did we get? You can tell me.
0.0112.
Did we all get that?
Yeah.
0.0112. So what's that? 11.2 milliohms? Yes, correct? Yeah. Jerry, did you get that answer?
I think
Well, there, let me show you. Okay, what was the constant for the copper, or the nichrome? 10 power... Hold on. 10 power minus 6, yeah? And then the length, how long is this wire? 0.2. And then this will be pi r squared. And this is over 2. And what is it? 5 times 10 to the minus 3. Yeah. 11.2 milliohms. That's okay? Absolutely okay, great. Okay. So I'll let you try these questions for a few minutes. What time are we at? Okay. Yeah, try these for a few minutes and then you can take a little break. As you can see, they're not difficult. You'll do these in like 4 minutes. There's only 4 questions. Once they're finished, you can take a break, okay? Wearing sandals on a day like today. This is why you get sick.
No, this platform like this today. It's so cold today. I want to complain about this. Yeah.
what's wrong?
This room.
Too cold.
Maybe it's sick.
Can you keep this for Bruce, please? Maybe he'll show up.
Maybe no heater?
The heater's on.
Oh, but it's not working.
Oh no, it's empty.
Yes. Oh, you can come early.
No, yeah, I know.
One. You also move it so big.
Yes.
Keep it in a very good way.
Yeah.
Meaning, okay, the notes before you so that we are receiving the way you want to.
Yeah, I'm comfortable up here. This part of the room is nice, yeah.
So,
What to do?
why?
Yeah, I know, and it doesn't help that the window's broken as well.
Yeah, so that's all.
Okay, look, I'll email the principal right now so I don't forget. I'll tell her that you're cold, the window's broken, and needs to be fixed. Okay.
Fix
Fix the back.
Oh no, that heater.
It's a molding button.
No, that heater never works.
It's a bigger.
Yeah, that's your shirt smell down.
This
So
one's
make that
bigger.
work.
No, that's...
Change a new one.
Okay, well if we need a third heater, I can ask for that too.
Oh, it's back.
If we have 4 heaters, we'll be sweating. Be like...
No, it's not all.
We can turn off it, don't worry.
Because that's small as it's supposed to be.
Okay, look, I'll email. Try these. Who's the class rep, by the way? Okay. Could you also ask Victoria to say something in the next meeting? If the principal hears it from 2 different places, it will get fixed quicker. I probably shouldn't have recorded that. Oh well.